This is another video in the Combinatorics sequence, but this one is not so much about the book. This is really about the code that I wrote to validate my answers to the earlier exercises. So in the previous video, I did exercises 1.1.5 to 1.1.9, and some of them were slightly complicated, and I wanted to make sure that I was getting the answers right. So it seemed like a good idea to basically simulate the sort of combinatorial events or generating process that was showing up in them, and to try to sort of like grab out those that are, that have the property being asked for in these exercises and count them up, right? Kind of just do it by brute force using a computer. And so I thought that basically the code that I wrote might be valuable to the viewer. I don't know if that's true. Maybe you want to make your own code, or maybe the logic behind how I built it is valuable, but one way or another, this video is all about the code. So here, I'm not even really going to talk about the old code, right? So this I showed in a previous video, and this was the way that I initially thought to sort of execute on this whole plan. But I came up with a better way to do it, so this video is basically just going to skip over the old code and move into the new code. In particular, I started designing the new code when I hit exercise 1.1.6, because this required me to simulate entire 52 card decks, or decks of cards. And looking at lots of rearrangements of these, my computer quickly ran out of memory. So I had to switch to a sort of way of doing it by way of iterators. I've used the word generator throughout here, but really I think you would call these iterators. In any case, the idea being that I can generate the next item, right? Even though technically these things are sets and don't have order, it's nice if you can kind of give them an order so that you can generate the next one, and then upon needed, remember where you were so that you can get to the one after that, and so on. And what that does is it saves your memory, because you don't have to have the entire collection all at once. You can grab a single individual, make a decision about what to do with it, which might be to print it or write it to a file, or do whatever you want to do to it once you have it. But one way or other, then count it, and then throw it away and generate the next one so that your memory never grows too large. So that's why I wrote this new, better way, especially to handle this particular problem. But in general, I think it's just a better way to approach the whole thing anyway. But then it becomes a real challenge. How do you actually decide, given a current state, right? Given a current combinatorial event, so to speak, which is like a tuple. But anyway, how do you use that to determine which one should come next is sort of the programming challenge here. And so the rest of this video kind of describes the various combinatorial events that we will want to generate in the future, and how to do that in an iterative fashion. Now, in fact, not only is this video only about the iterative method of generating these things, it's going to take a while to describe them. I'm actually going to describe them in some level of detail, how I built these, and so the videos take a while, and therefore this video is going to be entirely dedicated to just the first one, which is the Cartesian product. So this class that I have up here is meant to simulate the Cartesian product. Now, that's actually not the one I'm going to use in exercise 1.1.6, but it's kind of the simplest of them, and so I figured it was a nice starting place, and I'll probably need it, and I know I will need it eventually in one of the problems, so I figured I would start by designing this one. So, what is the Cartesian product? How do you model this? Well, an input has to be a list of sets that you are taking the Cartesian product of, so that, right, whenever you create this thing, you have to initialize it with a set list. Now, so that's a list, and each thing in the list is a set. out of some amount of laziness, I chose to just represent these sets as lists. So this really is, in Python, this is just a list of lists that you input to this class when you construct an instance. Okay, I'll just briefly describe the initializations of some of the fields. So here, of course, I just saved the set list. Now here, I create a list of indices, which I call current index, and it's initialized to 0 for every one of the sets. And somewhat intuitively, that means that this kind of represents the first tuple, or at least the indices to get the first tuple. So to get the first tuple, this represents that I would take index 0 from the first set, that's the first 0 in this list. Then the second 0 in this list represents that I use index 0 in the second set, and so on. Here I create a max index list, which kind of tells me the maximum index that I can use for each one of the sets. So fairly obviously, that is the length of the ith set minus 1 for each I. And then I want a tracker to tell me whether or not I have yet reached the end, which is to say the last tuple, right? So once current index, right, once that variable is the same thing as max index, basically, or at least once you iterate once past that, it will set end reached to true as a signal that there's no more to generate. Okay, so next we're going to look at this step function. And the intention of this step function is to return what is currently located at the current index, and then also, before returning, to also increment the index to the next available index. So here the first few lines are basically just giving me short names of various objects that are fields of this instance. Here I save the value, right? I go and get the value at each coordinate in the current index, and I store it into a variable that I'm calling out, because I'm not really going to touch it until I'm ready to output the answer. So once the rest of the code is done, I will check to see whether or not this tuple has the given property, right? This function has an input property, which is the property you're trying to count up, right? So you're going to, that property, that variable, is actually storing a function which takes in as argument a tuple and returns back true, false, depending on whether the tuple has the property you're trying to count up. And so we check the property down here to see whether or not the item that we have found has the property. If it does, we return the item, otherwise return none. But before getting to that point, we first want to set the current index to the next available index. And intuitively what you want is you want to take the leftmost index and bump it up by 1. But the problem is, what if the current value stored at the current index in that position is the max index? Well, then you want to take it, set it all the way back down to 0, move this over by 1, and try to increment this one. But again, the same problem arises. What if you're already at the max? Then you want to take this one and also set it down to 0. Increment and do it all over again, and keep doing this as long as you have to keep doing this until you finally find something that can be bumped up. And of course, you may ultimately get all the way to the end and try to move to the next index, but there is no next index because you know that's the signal that you've now generated everything that can be generated, and you should, in that case, set the end reached field to true. And that's effectively what this does. So here we're initially probing the 0th index and checking to see whether or not am I already at the max index? And if I am, then we set it down to 0, increment, right, using the walrus operator, increment that variable up by 1, and check to see whether or not by doing so I have reached the final coordinate because, or sorry, if I have really gone off beyond the final available coordinate. If I have, that means that I have generated everything there is to generate and I set and reached a true. But if that never happened, I would like to basically increment at the earliest opportunity the index at this particular part of the current index. And so that sets the current index primed and ready to, on the next time this gets called, give the next tuple. Anyway, so I think that fairly well describes how the step method was designed. Okay, next I'm going to describe this next method. And this also takes an argument which is a property. And it's right next is basically going to call on step, right? So effectively next scans as long as it takes to find the next item which satisfies the given property. Now, if you don't want to specify a property, if you, right, like, you know, basically if you just want to take everything, which often you will want to do, or at least, you know, often enough that it makes sense to give this some kind of default value, then I gave it the default value of the function which takes any input tuple, right? So that I'm using the lambda notation for Python, and x here is supposed to be a tuple, although of course, right, I'm not going to use it because all I do is I output true no matter what x is. So, right, that basically just gives me a property that is trivially always satisfied. So I just take everything by leaving that at the default value. But if there are certain tuples you want to take and other ones that you don't, then you would set that property to describe the ones that you want to keep. And all of this gets passed over to the step function. So anyway, what this effectively says is, you know, so long as I have not reached the end, right, as long as there is more to probe in the sequence of indices, basically, then I want to take the next right step to the next thing and check it for the given property. Now, as we saw in the design of the step function or method, right, that basically returns none when we did not find something that, right, we got an object but it didn't have the property. So I want to keep doing this, right? That's why, so anyway, this says if it is not none, that's a sign that the tuple was what I was looking for, has the property I'm looking for, so in that case, I return it. But if it is none, then I keep doing this until the end is reached. Now, if I make it all the way to when the end is reached, I don't want to keep looping. I would loop forever if I kept looping. So once I reach the end, then I return none. So effectively, right, at a much more summary description of what this function does, if there is a next thing that has the property, it returns that next thing. Otherwise, it returns none. And of course, there's a fairly simple reset method here that is, I think, pretty self-explanatory. And there's the Cartesian product class. And you can see down here that I wrote some tests for this. So you can certainly like run the tests to sort of like play with it if you'd like to. Anyway.